One of the common consensus right now is we need to scale AI, the bigger the better. Hundreds of billions are being spent in hopes that we achieve AGI through scaling, yet no matter how good LLMs have become, they are still stuck solving logical puzzles that we unironically refer to as an AGI benchmark. But in the opposite direction of this scaling virus, a new fascinating idea has emerged in the AI research field. What if we just have a model that can think and refine an answer until it is confident to tell you the answer? So it all started with this research called HRM, short for Hierarchical Reasoning Model. This model came out of nowhere and suddenly became comparable or even outperformed state-of-the-art LLMs from OpenAI, xAI, Anthropic, and Gemini, scoring a staggering 32% on ARC AGI benchmark and solving Sudoku on levels that current LLMs can't even compete with. But what's actually the highlight about this HRM is that it is a model with only 27 million parameters. Million, not billion by the way. With GPT-4, which has a known parameter count of at least 1 trillion parameters, 27 million parameters is like 35,000 times smaller, yet it is going head to head with the giants on this AGI benchmark. This sentence alone is already clickbait enough. Of course, the community would go wild when this just came out, but it got even crazier. Another improved version called TRM, short for Tiny Recursion Model, was published 1 month later that stretches the performance while being 4 times smaller than HRM. So what is going on? Has scaling AI always been the wrong direction? Well, today I'll be demystifying this hierarchical or recursive model for you, as we'll find out how this recursion model actually works, how impactful this model really is, and what it could mean for the future of AI paradigm. And before I dive into it, with how fast AI research is advancing but how slow the public is adopting AI, there has never been a better time to ship an app or start an AI business. But starting a business isn't easy. What's a viable idea, a sustainable business model, or simply what would actually work? These are all the questions you may have when starting out. Well, there is a faster way, which is to learn from what's already working. Especially if you're looking to learn from real examples, this free playbook from HubSpot called the AI Business Playbook shows you 7 AI companies that turn simple ideas into millions. Inside, you would understand and see how a 16-year-old turned a camera to calories demo into a 24 million ARR app in 10 months by advertising very cleverly. You'll also see how a college writing copilot grew to millions of users by zooming into citations and plagiarism checks instead of trying to be the everything writer. And my favorite part is how it breaks down the patterns across all these companies, like how they all used existing AI tools and just focused on solving real problems. So if you want a closer look at how people are making successful AI apps, check out this free playbook using the link down in the description, and thank you HubSpot for sponsoring this video. Anyways, the illusion of the ARC AGI benchmark is that it makes every model competing on this benchmark seems like they are all on similar capabilities to LLMs like ChatGPT, being able to solve math questions, writing scientific essays, and trade crypto at 20 times the leverage. But in fact, there are models on here that are not language models, with it being solely made to solve puzzles in a highly restrictive domain like ARC AGI. If you don't know what ARC AGI is, it is this benchmark where AI has to find a pattern in some example grids and predict how a given grid would look like by understanding the example pattern, very similar to what you would see on IQ tests. And unlike other language models, these tiny recursive models are trained specifically to solve a task like ARC AGI and other logical puzzles. Its in and outputs are just the color grid itself, and it is incapable of generating words or do other fancy stuff, which you could say that we did not arrive at some sort of super intelligence. But what researchers actually discovered is a highly efficient model that excels at solving logical problems under a highly restrictive and clearly defined rule-based setting. So if you compare it apple to apple with a generalizable monster of an AI god that can understand natural language and do pretty much anything, which many people believe are conscious and is going to destroy everything eventually, it doesn't make much sense, right? So let's step back a bit. What's actually really impressive about recursive model is that it proved hard logical problems aren't a domain only solvable by LLMs. Small models are capable too. And the highlight is no other small models have ever come close to performance this crazy. So how does it achieve this? The idea first gained attention with the release of HRM, short for Hierarchical Reasoning Model. It doesn't really explicitly say that it's a recursive model, but the logic is similar. And this paper kind of just blew up as the research was able to achieve 32% on ARC AGI, which has a better score than Claude 4 Opus and GPT-5 Mini Low. And it also achieved 2% on ARC AGI too. All this with only 27 million parameters. It's able to solve all those questions thanks thanks to its recursive property. It tries to reason internally instead of predicting everything in one forward pass. Like if an LLM has to calculate 1 plus 1, it can only spend the same effort to compute the equal sign and the answer too. But it is obvious that the computational effort isn't the same for both of these tokens, right? So what HRM does differently is that throughout its internal steps, it keeps an internal latent state that represents the reasoning process, which will be repeatedly refined into an output. So when a calculation requires more effort, it will be allocated accordingly. And this is achieved by using two different small transformer networks that run at different speeds. One low-level network which would update fast, and another high-level network that would update at a lower frequency. More specifically, it works by having the fast network tweak a hidden scratch pad a little bit every micro step by using the current input and the current provisional answer. And after several fast tweaks, the slow network wakes up, reads that scratch pad, and makes a bigger strategic adjustment to steer what the fast one will do next. The slow part also consults a halting head to decide whether to keep going or stop. This alternation continues with low-level network refines details, high-level network sets directions, and checks if the answer looks done. For training, right before running through a high-level loop, the method will wait for the fast loop to settle to a stable state, then computes gradients as though it is stable, instead of backpropagating every micro step to save compute. At runtime, it still performs a small number of these fast-slow cycles on the actual example and uses the halting head to pick when to stop and read out the final answer. These two networks work together just like the temporal separation of our brain, which the author took inspiration from, with the design being tied to how our brain has a multi-timescale cortical process and hierarchical depth, hence the name hierarchical reasoning. The paper even adds a brain correspondence section that compares HRM's representational dimensionality against mouse cortex in order to justify their design choice, which I'll get to later. While this idea was well received, especially with how well it performed empirically, some researchers are still a bit dissatisfied about the ambiguity that the HRM paper has. A heavy use of heuristics were applied on quite a few things, with the biggest iffy points being like justifying this 2 timescale design with biology and perhaps drawing similarity to a mouse brain may be too big of a reach, as the similarity is not proven mechanistically nor empirically, with the main reason behind the connection being simply they just look similarly organized in the latent space of the model versus a mouse brain, which you could say it's a decent amount of equivocation. Another point is how the abstraction of the hierarchical element in HRM is purely heuristic based. HRM is only being interpreted to do hierarchical reasoning over latent space. It is not really being proven that it's actually doing that under the hood. So the design could have multiple levels of latent features, not just only 2. On top of that, HRM's training assumes the faster inner loop has reached a steady state, aka an equilibrium, and computes gradients as if it was already there. But in practice, the loop is only run a few times and usually hasn't settled, so this shortcut can misestimate the true unrolled gradient. So the assumption and explanation is kind of weak to prove that the training works in theory, well, at least consistently work. But the results did prove to work, so who cares? Well, actually, this researcher called Alexia cared a lot and wrote another paper called TRM, short for Tiny Recursion Model. Also fascinated by the idea of HRM, Alexia wanted to address these weaknesses that it has and decided to take the matter into their own hands. First of all, to justify the use of a higher and a lower frequency network, a biological analogy may not even be needed. Alexia justified in TRM's paper that you only need 2 working memories with different rules, a higher level thinking space like a scratch pad and a placeholder for answers. It's a clear functional separation and not a biological one. If you collapse them into one state, the thinking scratch pad and the answer placeholder would interfere with each other, and if you add more states, you are basically adding more control knobs that do not really help on small data, and you make learning less stable. And this is also proven empirically in their result. So the logic of having the scratch pad updates a few times first, then applying the update to the canvas, and repeating this process a few times is how TRM is able to solve ARC AGI questions. As for addressing the assumed equilibrium in HRM during training, TRM proposes that there is no such thing. It trains on the loop it actually runs. HRM pretends that if you let its fast inner loop run long enough, it would eventually settle into a stable state, and then it takes gradients as if that stable state already exists. This assumption helps to keep the memory low and also fits into that 2 timescale narrative, but like I said, it may learn from the wrong gradients. And TRM does not assume the loop will eventually settle. Instead, it literally runs its own update loop a small fixed number of times and then reads that output it actually produced on the last real pass and backpropagates through that. They wanted a behavior that is to polish the canvas a few times until it looks right, not to pretend it ever reaches an exact equilibrium or a stable state to learn from. So with this model setup and an even smaller model size sitting at only 7 million parameters, which is nearly 4 times smaller than HRM, it is capable of achieving a jaw-dropping 40% on ARC AGI 1 and 6.2% on ARC AGI 2. This score has beaten the likes of Gemini 2.5 Pro, O3 Pro High, and just slightly behind GPT-5 Medium, which is really crazy. And all TRM does is that it just recursively thinks and refines its answer, and once it crosses the confidence threshold, it shows you the answer. What's even cooler is that for tasks that require less context length, input complexity, or expressiveness, like solving a 9x9 Sudoku puzzle, TRM actually performed better without using attention and only using MLP. But when it gets to a maze or ARC AGI, which is a 30x30 grid, attention-based TRM performs better instead. An explanation proposed by Alexia is that this is because self-attention is much better at long context. Well, as you can see how good LLMs are now, but MLP can still perform better because it is still much more generalizable and flexible, so it actually scored higher when context length is not too overwhelming. Another fascinating empirical observation is that when they tried to scale the model up from 7 million parameters to see how the model would perform, they found that adding more layers did not help the performance and increased overfitting. On the contrary, by decreasing the layers and increasing the recursive process of TRM, the model was able to perform better. So this is why they end up with a 2-layer model instead of 4 or 8 layers, as 2 layers somehow generalizes better, and the difference is quite significant. 79.5% for 4 layers versus 87.4% for 2 layers. This is completely opposite to what we observe in modern LLMs, where generalization scales proportionately with model size. A potential explanation for this is that why larger model size would overfit is because the training data is scarce. So by having a smaller model, it is much harder to overfit when the data set is small, which in this case works perfectly. And by being recursive, it solves the problem of trying to do everything in one shot. And as the recursion turns the job into a sequence of small reusable edits on a canvas, not having too many parameters is a benefit, as the model is harder to memorize the data and easier to generalize. This results in a model that can stay small enough to resist overfitting, yet still has enough iterative thinking to solve rules that a single forward pass from a small network would miss. Pretty cool, right? So yeah, I am very curious what the ceiling of recursive models can be and how we can improve from here on. What do you think? Let me know down in the comments. And if you like today's video, definitely check out my newsletter where I cover the latest research papers weekly. On there, you'll always be up to date on the latest research progress. And thank you guys for watching. A big shout out to SpamMag, Chris LeDoux, Deagan, Robert Zawiasa, Marcelo Ferreira, Poof and Inu, DX Research Group, Alex, and many others that support me through Patreon or YouTube. Follow me on Twitter if you haven't, and I'll see you in the next